Right, you can see my screen, right? I'm just going to give a very, very short, okay, it's not going to be short, sorry. I mean, a very, very rough talk about the work that I did the last 2 weeks because Sharon asked if I could do a sharing about this. Right, so first, quick introduction to the problem. We have this smart contract we use in Trade Trust. It's called the title escrow contract. And what is it used for? It's actually used to hold ERC721 tokens. You call it in escrow, right? But basically, what it does is it allows us to create constraints around what you can do with the token, right? And we want to do that because we want to create these extra, what do you call it? Roles, right? So with a normal ERC721 token, what you can do is you can just, as there's only one role, the owner of the token, you can transfer it, that's all, right? But we wanted like additional roles such as you can hold stuff, but without owning it, right? So that's a bit different from like just owning it. So reasons like this lah. And why does it need to be optimized? It is because we actually deploy a copy of this title escrow contract for every single ownership change, right? So for example, when you mint it, it goes to a title escrow first, right? Then if you want to transfer the second owner, then it has to be a new title escrow has to be deployed. So this is a design decision. Like we could actually create a global one that keeps track of all of them, but that was a decision we made against because it's a bit iffy. Like you would like track everything in one global contract, right? So and also it becomes very messy. We have to keep track of like this global singleton, and then all the state is inside. And what happens when you upgrade and all that stuff? So we decided, every ownership change should have its own title escrow, and that also makes it very clear that this title escrow is only one use. Right? You transfer into it once, you transfer out of it once, it cannot be used again. Then the audit trail is very clear, right? When you want to look back on your endorsement chain. So that was the design decision we made. So, but then what? Now it's very expensive, right? I think at the peak, 2 months ago, Shuqing was telling me people are complaining. You make a transfer, it costs $200. How's that acceptable? So that's not acceptable. Right? So it was very expensive because gas prices were high and everything. So today it's about $50, which is still quite expensive. So why does it need to be optimized? Well, because $50 is not an acceptable cost for a transfer. Right? So how can we optimize this? Actually, the implementation itself, right? Like what I had to do is very simple. You'll see later on my last slide. You'll ask, how come I took 2 weeks to do that? Right? But I'll explain how it works first, right? So everyone understands it's not just a magic black box. Okay, so I'm going to talk about this part, which is introduction to proxies. Sorry, my slides are like super rough. I was writing in my notes app, and then I realized I can't zoom in on the images, so I had to export the PDF, and it looks like a mess. So this part is about proxies, but first we have to talk about like what an Ethereum virtual machine is. So the Ethereum virtual machine. So you know that there are many Ethereum nodes in the Ethereum networks, and like there's like mainnet, Robson, Rinkeby. Each one is its own network, right? And all of them executes smart contracts, right? We just say they execute smart contract and then it works. But actually, what's going on when you write like Solidity and then you deploy it? I'll talk about very briefly cover like how it all works. I'm not going to go into like super detail. I hope I get everything right because I'm also like not very clear on like the exact details. Right, so so each node runs a virtual machine in order to simulate what happens when a transaction runs. Right, so when transaction runs, you get like a bunch of you get a bunch of like code that runs, and then you have the before state, you have the after state, right? So the smart contract determines what happens from the before to the after, right? So and it does this by way of using a Ethereum virtual machine, and the code that's run is actually Ethereum assembly, Ethereum opcode, but we write in Solidity. Right, Solidity is it looks like C or JavaScript, very similar. It was a design decision they make because they wanted it to look not too foreign. Right? But there are other languages like Viper as well, and a few others, but I don't even know about them. So, but the most common one is Solidity. Right? So you write that, and then it gets transformed into opcode, and then stuff happens. What happens? So the Ethereum virtual machine, the architecture of a virtual machine actually is not too different from your normal regular computer. You have a program counter, you have a machine, it has a stack, it has memory, and then it has storage. Storage is like your hard disk, right? The memory is like your working memory, your RAM. Stack is basically what's going on in your processor, like the working memory, right? And the one thing that's different about EVM is it has this thing called gas. I'll cover more about like what's this gas later. I mean, we always talk about like gas is too expensive or all that stuff. I'll explain like how a gas cost comes about. Right. So it's if you've studied computer architecture in school, then this should look quite familiar to you, but you don't have to remember this. I can't remember either. I just like this. I prepared this in like 1 hour, so I just basically went and Googled stuff and I took screenshots of everything that I needed to show. Right. So we talk about like executing like smart contracts runs in the EVM. So what is being executed? Bytecode is executed. Right? You always see like when you run Ethereum transactions, you go on Etherscan, and you see a whole bunch of like hexadecimal, and what's going on there. So you can see that it's actually just bytecode. You don't have to be too scared of it. You should be like, if you're working with bytecode, you should be scared of it. It's quite intense stuff. Raymond's good at this. I'm not so good at this. Right? But it's basically a bunch of like instructions encoded into hexadecimal about what the machine should do. And it will look quite foreign if you've never done assembly before, because like Solidity that's compiled into bytecode, it's very hard to understand like how it happened if you've never like done it by hand before. But yeah, so like if you look at the Ethereum, the Etherscan, sometimes you see like input data, right? And you see like all this 0x something is you can just see that, push one command is actually 0x60, right? Then after that is just the data. So it says push one of 0x01, right? And blah blah blah. Yeah, that's just the bytecode what's going on, right? Then we talk about deploying smart contracts. What actually happens when you deploy smart contracts? So when you make a transaction, it's just data, right? It's just a bunch of data. But the difference between a contract deployment and a normal transaction is that the contract deployment doesn't have a to address. Right? The to address is actually left blank if you look at the transaction data. So that's how the EVM knows that, oh, this is actually a deployment. So you can think of a deployment as creating a new class, right? Like when you instantiate a new class in JavaScript or Java, and then a constructor runs, and then after the constructor runs, like you have an object, right? So what actually happens is that the constructor runs, and then the constructor generates a set of runtime bytecode that gets stored into the state in the Ethereum memory space, right? The global memory space. So that's what happens when you deploy, and then you get a smart contract address. So at the smart contract address is actually the runtime bytecode. Okay, so whenever you're thinking, oh, what's going on when I put in an address and then I just like magically call functions, right? That's actually what's happening. You're actually calling the runtime bytecode that has been left there after the constructor has executed. Right? Yeah, so that's what I just explained. Stuff. Okay, then what happens when you make a function call? Like, so you remember I was talking about like you deploy a contract. Then what if you're not deploying a contract? You're making a function call to an address. You put an address. You say I want to run this function that's at this smart contract that's at this address. So when you make a function call, it's actually quite interesting how it works. First, you have to compile the function call, and this is actually what goes in. There's the first 4 bytes is actually the function selector. And the function selector is actually just the hash of the function signature, right? So for example, if I want to call like the balance of function, right? So the function selector is actually literally the hash. Did I write it down here? I think I did write it down. But yeah, I'm actually just calling the hash of literally the string of balance of bracket address, right? And then we take the first 4 byte of the hash, and that's the function selector. And that's actually how the EVM knows what function you're calling, right? So it actually goes through the code that's at the address and looks for the matching function selector. And when it finds it, it will execute the code there. If it doesn't find it, then it will fail. You'll get a revert. Right? And what's after the function selector when you make a function call is actually the function arguments, right? So when you call like a function, you have like parameter A, B, C, D, right? So that's just encoded and then stored as call data, right? So then this call data is actually stored in the stack when it executes, right? So if you think about it, when you run a function, you have like the memory and the variables and the scope, right? So when the arguments are passed in, it's actually stored as call data. And I'll talk more about this call data very shortly because it's important to the proxies that we're going to talk about. But first, let's talk about memory storage as well, which is also important for understanding how proxies work. Right. So for a smart contract, how do you actually store data? Right? Because when you make all these variables in the smart contract, then the data has been stored somewhere because you can somehow retrieve it in a subsequent call, right? So it's actually persistent state. It's like storing it in your hard disk. So every address actually has like a bunch of memory, and they're actually called slots, and they're numbered literally from 0 onwards. And each slot size is actually 32 bytes. Right, that's why you see sometimes you're wondering like why the sizes of things are what they are. For example, bytes 32 is one slot, right? And this is not very relevant, but it's a useful trivia. Storage can be optimized when the data is less than 32 bytes. So if you have two 16-byte data, you can actually fit into one slot. But that's not so important right now. Okay, so that's how data is stored. Every smart contract address actually has its own memory space, and like data is stored inside. Okay, so let's talk about call versus delegate call. So when you make there's these two opcodes, they're called call and they're called delegate call. So call is your normal function call. When you call a contract, all right, and then it actually executes stuff in it, right? And the difference between call and delegate call is that delegate call actually, you can think of it as you are executing the code of your target contract, but in your own context, right? So versus when you do a normal call, right? When you make a call, the context actually changes because your stack is you have more layers to your stack now. You make a function call, you repopulate the memory, right? So that's the main difference. And this is important because otherwise the target contract cannot modify stuff in the caller's context, right? So if you think about like in JavaScript, when you call another function, that function you can't modify the parent variable unless it's specifically allowed to. So I think actually in some languages you can't modify the caller state, right? In fact, you can't even pass stuff to the child for some languages. That is the case for Solidity. So unless you use a delegate call, right? So for delegate call, what's happening is actually you're basically inlining the target contract's execution back into your own function state, your own function context, right? So that is what delegate call is. So this is actually how proxies work, right? In the sense that you have the proxy is the caller contract. So when you call the proxy, it actually just delegates everything to implementation, right? So it executes everything from the implementation in its own storage space. then it's when you modify like variables, it's actually stored in the caller contract instead of the target contract, right? Long and short, that's how the proxy works. Now let's talk about like the cost of interacting with smart contracts and why proxies actually save gas. Right. So actually running code is quite cheap, right? If you're just running stuff without storing anything. But then when you are making memory changes to the Ethereum global state, that's when stuff gets really expensive really quick, right? So like for example, S-Store is storing data of I think it's one slot, right? And there's 20,000 gas really. I don't remember what that is in dollars, but it's not cheap. I'll remember later. Right. So when you execute like a function call, like it just keeps running all the opcodes, and then like remember earlier in the virtual machine diagram, I think there was a gas counter. Is there? Yeah, there's a gas available counter. So this gas available counter actually is populated with your gas limit, right? When you send your transaction, and when a transaction like executes until the gas has finished, but the code hasn't finished running, that's when the transaction fails, right? So like all the codes just cumulatively gets deducted, and then at some point either the contract finishes or like the you run out of gas, right? And this is also like taken into account when you are deploying smart contracts, right? So if you think about it, like if we're deploying a new title escrow every time we make a transfer, that's actually storing a lot of data on the blockchain, right? Because all the function code is actually all the same, but uh, we have to store it every single time just because we deploy a new smart contract. So that's like it gets really expensive really quick. Because we're storing like smart. That's why I optimize it using a proxy, which means that actually I'm deploying a very minimal, like just a sort of a redirect, a redirect that sends the calls to another implementation. So every time we make a transfer, we actually only need to deploy the proxy, and that's a lot cheaper. How much cheaper? We'll see later, right? So actually, this is it's actually such a useful pattern that it's been formalized into a Ethereum improvement protocol, right? So it's actually called EIP 1167. Right?
We can't hear you anymore.
You can't hear me?
Yeah, I can't hear you. So anyone has this problem?
Yeah,
sorry. Is it working
30 seconds or so, yeah.
Oh no, where did I stop?
The proposal.
The EIP proposal, isn't it?
Yeah, it got refactored into a proposal.
Yeah, so sorry, I don't know if I got disconnected. I just got too far from the mic. I actually started sliding backwards. Okay. Right. So EIP 167 is it's such a useful pattern that actually got formalized into a Ethereum improvement protocol, right? So and it's called EIP 1167, and it's actually a very short string. I don't know if I have an example somewhere. I don't think I wrote it down, but it's actually a really short string. It's like barely longer than the rest, right? So that's the EIP 1167. It's very minimal, and it's actually a whole bunch of it is actually written in assembly itself. It's not even written in Solidity. Like it's so optimized, right? And Open Zeppelin actually has a if you look at our smart contracts, you know that we import a lot of code from this library called Open Zeppelin contracts, right? That's because they write code that's been audited, right? So They've been audited like for security and for correctness, and they tend to not have issues. Don't know if anyone has ever had issues before. I don't remember, but yeah, they have quite a good track record. So they have this one of their utilities is the clones, right, which is basically the EIP 1167 proxy, right? And this is how you use it. Like you just import the clones, and then you call clone on the implementation, right? There's a few other functions. So the one is clone deterministic, which means that you can actually create a proxy that is at an address that can be, you can set the address. Basically, long and short, you can set the address. Whereas for clone, the address is randomly generated, sort of randomly, right? So there is some gotchas to this, right? So remember earlier I talked about like the constructor. The constructor runs, and then the runtime bytecode is generated. Right? So, but then in the case of a clone, there's actually no constructor to run because the implementation was deployed a long time ago, and the constructor in the implementation isn't run when you clone it, right? Because we are just doing a delegate call, right? We're just passing we're just forwarding all the calls. So the constructor in the implementation doesn't run. So you must actually use a manual initialization, right? There's no fixed name for it. But I think convention is to just call it initialize, right? And one thing you really must make sure is that the implementation is safe from modifications, right? There was actually an exploit once when somebody did use a proxy, but then he forgot to protect his implementation from modifications. So like a hacker came along and realized, hey, I can actually change the implementation. And if I remember correctly, a big sum of money was lost there. So that's dangerous, right? But other than that, it's quite safe to use. And now to the end is how did I implement it in title escrow cloner? Actually, oh shit, this is way too small. But you will see it's actually really simple. Is this big enough? Right, so on the left is the original. On the right is the one with proxies. On the right is the proxy. So you can actually see I have the same function, deploy new title escrow, because this is what we call, right? The difference is what happens inside and also in the constructor. So in the constructor, I actually create a new smart contract, and this is actually my implementation address, right? So I create a blank one, and then after that, we just create a clone whenever we want to deploy a new one, right? And that's actually just deploying a proxy, a very small proxy, and then we call initialize on it. On the left, you see that we actually call a new title escrow, right? This is the original code. We initialize it with all this stuff, right? On the right, we call the initialize on the proxy, and actually it's exactly the same. It's actually quite simple to implement, right? I actually spend most of my time not doing this. I spend most of the time tidying up getting the repo in a serviceable condition. It was quite outdated. A lot of things had to be updated, right? So the result of all of that was that the cost came down, right? So you can see the original cost of a transfer to new title escrow actually cost 1.2 million gas, right? Which is about 52 USD. And then in the new one, it came down to 240,000. So that's about 5 times savings, right? That's because we don't have to deploy the contract code anymore. All right, so that is it for all the technical stuff. Let's see, we have some questions. I have one question from Ryan. The proxy will be updated to the newest address of the target every time there is a change. No, that's not actually what the minimal proxy does. There is this option if you use Open Zeppelin upgradable smart contracts. You can actually change the implementation. But for the minimal proxy, that's not an available option because we want to maintain that it's immutable. You don't want to let people change what's going on. Right? Does that answer your question? Okay. Anyone else has any other questions? It's a bit of a very technical talk. So long as question. What do you mean when there's some price variation?
You scroll down a bit.
I think like the other function like transfer to.
Oh, okay.
Is it? Yeah.
Yeah, so this is expected because actually all the calls are going through a proxy now. So it's slightly more expensive because there's a little bit more stuff to do. But so this is actually a trade-off. If you find that what you are mostly doing is just running stuff without deploying new stuff, then maybe you shouldn't be using a proxy. But for us, the majority of the cost is actually in deploying. So that's why.
Okay.
Any questions from Chandran?
No question.
Okay. Yeah, it's quite a complicated topic, but actually, if you see the implementation is actually like really simple. So that's really good. Like it wasn't difficult to implement. It's just that to understand how it all works is a bit complicated. Okay. If there's no other questions, then that's all from my talk.
Thanks.
I guess there's no one else, right? So I was the last one.